everybody. This is a talk about how to cut to the chase with natural language processing and natural language understanding. Just to kind of calibrate where we should spend our time today, by show of hands, how many people here are pretty comfortable or at least have some familiarity with techniques like word-to-vec or word embeddings? Awesome. Okay. Cool. So I was part of a company called SkipFlag, which was acquired by Workday about 3 months ago. And SkipFlag is a smart knowledge base that builds itself from your workplace communication using deep learning. And what that means is that, so we have a product hypothesis, which is that the structure of your business is very difficult to understand from your locally constrained perspective, and that this is similar to other systems like traffic or the economy, whose behavior and dynamics exhibit an outsized influence on the course of our lives, and that like in the marginal projections, so if you imagine high dimensional data and you're projecting it onto the margins like a histogram, you can see shadows of the actual structure, and that the people you do business with and work with are different than the people that you have links to in your org chart. And so we think about capturing across all of the information streams that are digital byproducts of you doing business, like Slack, like your GitHub commit logs, the wikis you edit, the meetings you attend. All of this information captures the implicit aspect of your business. And we joined Workday to weave together technologies that understand these implicit structures and can allow you to connect with information that help you become unblocked. So that's expert identification, natural language question answering. So if I say, how do I mount an elastic block store volume on my remote development server? If somebody's already answered that question in Slack, they've probably done it 20 times, we should just be able to connect you with that answer right away. And failing that, back out to expert identification. And so we connect natural language, this unstructured text, to a knowledge base that understands the world at large, as well as the structures and relationships inside of your business. So if, for example, the Apollo project means something different at Workday than trying to go to the moon, we can understand that distinction and semantically disambiguate utterances of the same word based on their context. So this talk is about some of the technologies and practices that we came to favor in the course of building production machine learning systems under the gun, and what for us personally at least, we're at relatively high stakes. And you don't have time to waste, and you just need to get it done fast. So one of the first insights that I think is important to share is that, particularly as regards production engineering and machine learning systems that actually are being used by, in a customer-facing capacity, you need to stand up a model as quickly as possible and get that pipeline running. So we typically had like a 2-week by 2-week research and development process where we would spend 2 or 3 weeks investing in reading papers, doing a survey of the literature, using Python notebooks to kind of stovepipe together models, and then we would spend 2 to 3 weeks productionizing these models and bringing down the compute overhead and just kind of tightening up some of the loose ends. And that process of getting it scheduled as quickly as possible so that you start to see where it fails and when it brings down the machine and just the sort of seams is really, really valuable. Additionally, I love this concept that, and particularly in a startup environment, I think there is a need to not necessarily fetishize the latest and greatest technology, but instead use something which is reliable, and particularly something that allows you to establish a reasonable baseline. So the third part of that R&D process I just described would be what I would call hardening of the system. And so that is, in general, looks like a Kaggle board style metrics hack, where you're just continually updating the model and you're saying, are we improving its performance on some reasonable train set or some reasonable test set? And what's nice about these baselines is that if you're not doing better than something simple, you really can ask yourself the hard question, which is like, what are we doing here? Is this worthwhile? Are we spending our time in a meaningful way? So when it comes to building natural language understanding technologies, you need a lot of natural language data. And some of the corpuses that we got a lot of mileage out of. So we built this company on public data sets. And I think it is great to leverage signals that exist in the wild because they capture how people actually talk. And each of these corpuses, and what's interesting about some of the decision making that you'll face when you're building these technologies is that the semantics of each of these different corpuses encapsulate different, like the Sapir-Whorf hypothesis, which is how you talk about things influences how you actually perceive the world. You see differences in these corpuses reflective of the kinds of utterances that people produce. And so Common Crawl, for example, is petabyte scale web crawl that's available on S3 for free. And it's multilingual, it has Unicode errors, it's the internet. It's tough. It's a lot of non-grammatical text, which is great if you want a robust algorithm. This is in contrast to, for example, to something like Wikipedia, which is written in a very artificial style, but is relatively comprehensive and in general has a nice character in that people are speaking in the sort of Oxford English Dictionary, what are the rules of grammar? The MLA style. And it's also taxonomic, so it's that hyperlink structure and some of its connection to assets like Wikidata are really, really valuable. And Twitter sits, it's just how it's doing its own thing over there. And what's great about Twitter is that it's just highly non-grammatical and it's really sparse. So your model trained on Newswire corpuses will probably not generalize to Twitter. And so it's a great stress test for any technology that you're trying to stand up to see, does this really understand across domains? Twitter is particularly valuable for that. But what's interesting is if we look at, and I think these are glove embeddings from the Stanford NLP lab, and we'll get into some of the details around these embeddings. But if you look at the words which are semantically nearest in these high-dimensional embeddings, dependent on the corpus that the glove algorithm was trained on, you'll see that it captures the texture of that high-dimensional space reflects how we talk about certain things in this corpus, and even when this happened. So I think the Twitter corpus was probably cut shortly after the Occupy Wall Street protests, and so you have this reflection of these kind of like follow-on movements like Occupy Burma, Occupy Lebanon, that really are distinctive to Twitter. And so Wikipedia does not understand, an embedding fit on Wikipedia does not understand Occupy as a political term. And so if your model assumes that that will be true, you will have a difficult time teasing that out of the data. And so this is, I mean, the general problem, this is a special case of the general problem of sense disambiguation, but the choice of source data has an outsized influence on how your model is able to perform over time. So I think the next piece of the talk is really about kind of what it looks like to do this stuff. If you think about like the 2x2 grid of impact and ease, you want things that are high impact and also relatively high ease. And these are some of the technologies that I really like for just getting it done in prod. So just to kind of establish a shared frame of reference as regards kind of the historical context behind text mining and where deep learning fits into that picture. Historically, I mean, through the early 2010s, you had this model whereby documents were represented effectively like a bag of words, and the relationships between words were really not something we could say much about. And so the fact that azimuth and declination are both things that relate to orienteering, much less so percolate, is not something that traditional text mining techniques are going to capture. And so you have this document word matrix, which is several hundreds of thousands of dimensions and is highly sparse and does not have any of this correlation structure baked into it. And so using some of these traditional statistical machine learning techniques like latent semantic analysis or latent ratio allocation, you can condense that matrix down to just a couple hundred dimensions and capture the vector basis that is maximally descriptive of the structure of the data in a way that will say, well, azimuth and declination are kind of redundant terms. If I observe one, I'm much more likely to observe the other. I don't need two floats to represent this. I can just do it with one. And so these techniques will now give you, in general, some topicality as regards the content of your documents. And this kind of gets you to Amazon-style people also bought recommendations that you would see in like 2010, where it's like, yes, I can see why you think that. It's fine. It's not like brilliant, but it's okay. And so I think what the thing that you have in your target here is always the same, which is a matrix encoding features describing a set of documents. And once you get to this, where here, I guess we've done this with column vectors for documents, once you get to this representation, now you can open up classification, clustering if I'm trying to rank job recommendations, if I'm trying to recommend products or cluster documents into different categories. This is kind of the fissile material for that enterprise. And it turns out with deep learning, the exercise looks very similar. It's just the techniques are better. So what's neat, and everybody's seen, I suspect, given the show of hands, this example, which is that Word2Vec operationalizes this idea of analogical reasoning. And so that is to say that in this vector space, I've embedded points where in this, let's say 300-dimensional vector space, where terms that are semantically similar should be nearby one another. I'm trying to predict the context in which the words appear. And what's interesting, and this is like the king minus queen equals man minus woman, or king minus man equals queen minus woman, is like the classic Word2Vec analogy. And what that actually means is that here I have a vector representing king and I have a vector representing queen. And the difference between those 2 points is itself a vector. It's the third leg of that triangle. And that vector is the gendered, it's one aspect of gender. It's the genderness vector capturing the relationship between these 2 types of words. And that property generalizes to other relationships like capitals here. So I could add this geography relation, or this capital relationship vector to Facebook, for example, and I might get a word near Palo Alto, for example. And it also does it across, so there's these aspects, and then there's also the semantic and syntactic aspects, which is good, better, best. Those relationships are encoded in the texture of this space. And so you're really thinking about manipulating the texture of this space when you're making choices about what you input into these into the algorithm. So what this buys you is now a sentence matrix. So instead of having a document encoded in terms of a sparse vector of TF-IDF scores across terms, now I have a matrix where each column in the matrix corresponds to one of these Word2Vec embedding or glove vectors. And then I collapse that through some process. Could be centroid, TF-IDF weighted centroids, could be an LSTM, could be convolutions over this sentence. But I want to get back to that document feature vector, which gets us back to that document feature matrix, which opens up all of these downstream applications like clustering, ranking, classification. It's from Neuromancer, by the way. It's the opening line of Neuromancer. So I like glove a lot. You can, Word2Vec and glove are basically, they're fungible goods in the sense that your performance on these benchmark data sets is going to be basically the same regardless of what you choose. Glove is a lot more useful in practice because you can choose how many dimensions you want, which if you're operating in a resource, like a memory constrained environment, that's kind of useful to only bring on 50 floats for each term rather than 300. Additionally, they let you, you choose between the semantic structure of the underlying corpus, and it lets you make distinctions about casing. So with regards to sense disambiguation, Mike Conover title cased is a different token than Mike Conover lowercased. That's not really useful. I should be able to capture the semantic context in which both of those different tokens occur, regardless of the casing. So the fact that I can use lowercase corpuses is useful. However, acronyms like IBM or IT the word it, or US for United States, will be, you'll have a single point for the United States and for us, which is not necessarily very useful as a semantic quantity. So you basically can choose, depending on your application, a corpus, an embedding that's appropriate for what you're trying to accomplish. So let's say that you fit. I think I may have removed this slide on fitting embedding. So I like GenSim, by the way. If you're trying to fit your own embeddings or just want to manipulate these spaces and do some of this like vector math with a really nice API, GenSim is a great tool, but it has a restrictive license. So we didn't use it, but it's great. And let's say you fit your own embedding. I just want to make sure. Okay. Let's say you fit your own embedding, and you ask yourself, have I done the job correctly? Because this is an unsupervised algorithm or a semi-supervised algorithm. The TensorFlow embedding projector is a great tool in that it will, using these, what is it called? Is it manifold embedding? I forget. This is the t-SNE algorithm. Multidimensional scaling is another example of taking a high-dimensional vector space and projecting it down into 2 dimensions, or 3. Though I would never waste my time with a 3D representation. What's neat is that you get these tendrils that have, because this preserves locally, or the local structure of the high-dimensional space, what happens is that these tendrils tend to correspond to semantic units. And so an example of what you might observe if we were just looking at word embeddings is that you would have like numbers along one of these tendrils where we would have like the number 1, the character 1, then the number 10, or let's say the number 1 and then like the word a few, and then the word some, and then the number 5, and then the number 10, and then the number 100,000, and then the number 1,000,000, and then you might have the word bazillion. And that those are the same semantic units, and they encode concepts, even though one's a set of numbers, one's a set of letters. They're doing the same work. And so what you can do here is using this, and this is all semantic. There's not a, you're minimizing a loss function, but it's not necessarily going to give you good results. And so you really do this qualitative data analysis to get a sense for whether you're happy with what's coming out. And what's neat here is that I can embed anything, really. I could embed recipes, or the embedding projector supports natively images. And so I can interact with this embedding. And here I think we have documents from different languages. And if my embedding is behaving well, documents, translations of the same sentence should be nearby one another in this reduced dimensionality space. And in fact, that's what we observe. But this also supports out of the box, like I said, images. And so you can mouse over and get little thumbnails, and you're like, okay, it's a shark, it's a boat, it's the water, it's the coast, and it's like, all right, like it worked. And so this is a nice tool, and it's beautiful for working with these embeddings and sort of smoke testing whether you've done the thing that you hope to set out to do. So I think fast text is a great tool. I was talking about this with somebody at lunch. As a baseline to beat, it's really strong. It's a tool from Facebook. It has a really minimal API. You take a text file, and it's one tab. On the left side are the labels, and on the right side is the document. And you just feed it in. It produces embeddings, and then it produces a classifier that will categorize new text into any of the categories that you've exposed to it. And so as an off-the-shelf tool, if you're like, let's say I have customer support tickets, and I'm trying to rank which of these is most likely to get escalated, I should train a face text classifier and see what kind of performance can I get out of the box of a tool like this, and is there any grist for the mill as regards to this problem, and does it make sense to invest in building our own, or should we just package this up and ship fast text? It has a very permissive license, so you can use it in prod for commercial applications. And so what's neat about fast text, in addition to the fact that it just kind of works pretty well, is that it does what's called subword embeddings. And so this word up here, it's clearly a chemical, except for the fact that I made it up. That word doesn't exist. But we all kind of knew that it should probably be a chemical. I mean, the image aside. And so what's cool is that the structure where, with like tools like Word2Vec or Glove, you treat each word as an atomic unit of analysis. Fast text treats words as compositions of sub-charactergrams. And so basically, it runs a sliding window of various sizes over a word and can say the CHLO has a character which is suggestive of chemical elements. And you could also imagine the same thing for like startup names or even names from different countries, right? Like you can look at a name and say, that looks Portuguese, right? And it is the relationships between the characters which is instructive. And so what's nice about this is that it lets you learn embeddings for out-of-vocabulary words. And so if I fit a model on a corpus and I need to now generalize to novel text, fast text is actually very powerful at doing that. Starspace is another tool from Facebook that I'm crazy about actually, because it's a pretty smooth route. The documentation could use a lot of work, and I think the reason it hasn't gotten more adoption is that it is not as articulate in communicating what it can do as fast text, which is a shame because it's very, very powerful. And it operationalizes something known as a contrastive loss function. So in general, what a contrastive loss function tends to favor is putting points that are similar to one another nearby in this vector space and pushing points that are dissimilar to each other far away. And so what that means is that, let's say that I'm embedding, so if you can do this now, you can type into Google image search, picture of a man, man in a blue shirt standing in front of a horse. And it will show you pictures of men in blue shirts standing in front of horses. And it's like, how is that possible? It's crazy, it works. And I mean, I don't know this for a fact. I don't work at Google and I never have, but I bet that they're using contrastive loss functions where we are jointly embedding images and text in a shared vector space such that I have a bunch of images that people have labeled with descriptions of what's in them. And let's say that I get 10 people to describe what's in the image. Or I use like hyperlinks, for example, or the sentences pointing to those images as descriptions. And I want to put in this vector space the sentences and the images nearby one another such that I can now, for a novel sentence, I have some mechanism, kind of like what we discussed earlier, where I have this now sentence matrix and I project it to a document vector. And I can now take that document vector and I can say, give me the k nearest neighbors in this embedding space to this sentence. And I filter only on images. And what's neat about this, we talk about learning to rank, like job recommendation, ads. I mean, basically all of the consumer relevance technologies that you interact with regularly are learning to rank problems where you have a user, a personalization vector, and an item vector. What's neat about a contrastive loss function is that it will perform an implicit learning to rank as measured by Euclidean distance or cosine similarity. And so you can say, give me the things that are most similar to this, and it will automatically do this. And so you can perform collaborative filtering, you can do text classification, it works on networks, which is really powerful technology. Node2Vec is another cool tool for doing network embeddings. It also works for image classification. So it's, as a tool for measuring similarity and doing so in a very general way, Starspace is a really powerful technology. So I think that there are, what's that, 2 minutes? Yeah, we're right at the tail end here. Thank you. So much of this work is about not putting the cart before the horse. And the zeroth law of Wikipedia is that Wikipedia only works in practice, it never works in theory, which is super apt. And I think there are a lot of techniques mathematically in building production ML systems that have this character. And so, for example, taking the TF-IDF weighted centroid of your word vectors, I've had the discussion, I've had the argument about why that's just a bad idea. It turns out it works. And so, it's like you could, build out an LSTM-based model or do something more sophisticated if you're doing classification, but there are simpler techniques that provide that baseline, and that's what you want to get to, is that like fail fast, right? If this is just not going to work, tell me as soon as possible, because I just don't want to waste any time. Or if the off-the-shelf technology gets me 95% of the way there, and we can start making money today, maybe we don't need to invest. So at Workday, what we're doing, one of the themes that has characterized my work over the years is this concept of information flowing through society. And at Workday, we're thinking about the implicit structures. So this is the connections between employees of Workday on Slack and people who talk about the same things in the same forums. And this network characterizes, it has a hierarchical community structure. And this is reflective, and there's a geospatial component, there's also a topical component to this. And this is reflective of the fact that the people I do business with are not necessarily the people that I report to. So there's the org chart, and I think I need to move away from this analogy, but I'm not ready to yet. And then there's like the deep state, which is like, who's actually doing the work? And like, I think this is a much more powerful representation of an organization. So thinking about text as it flows through social networks and the conjunction of the two, I think, is a very powerful lens for understanding society at large, and particularly organizations. And we're hiring, so reach out if you think any of this sounds interesting. I want to thank an incredible team of collaborators, just the best people I've ever had the good fortune to work with. And I want to thank all of you for your time today.
Great, Mike, thanks very much. Time for a question or two before we get the break. Yes, sir, got a mic coming across, thank you.
Thank you for the nice presentation. Selfish question here. When you're classifying text data and you have a small data set, which we've talked about, and a small training set, what solutions do you have for that sort of problem?
Label more data.
Do you have any more sexy suggestions?
No, I do. It warrants touching upon. So one of the things that did not make it into this deck is that I think we nearly broke ourselves on the wheel trying to do transfer learning and find something that looked like our problem domain. And that works in a lot of situations, but sometimes the process of, especially when you're trying to operationalize taste, like, is this a good recommendation? It's hard to say, but the team knows. Having everybody sign up for like 6 hours of data labeling and doing that across a 6-person team, for example, can get you, particularly if you use techniques like negative sampling, where you say, I'm going to pick random examples, random pair. We can talk about it afterwards. I think I don't want to get into it on stage, but the idea of labeling data manually is very, very powerful. Even though it's a drag, it is super powerful. You're creating new information. And then regularization, just don't let your model overfit, look at your test error. Yeah.
Okay. Sounds like a conversation for break.
Yeah.
All right, and there we are, we're at 3:20. We will be back in here. Let me first say, Mike, thank you very much for your